Hello there guys, welcome back to another video. Now, just before we start, make sure that you fully open your work, so full open and full explanation and working out where needed. So this is why we're here for. We want to make sure that yes, we are getting the open, but we also need to know and listen to the explanation, so this way we know in the future how to get those marks, and then if we have any working out, we need to also show all the working out, and this way we know how to get all the marks in the future. Now let's go for question one. Now, question one we have is we have a snow buggy uh, being pulled by sail. Okay, so the buggy rests on the ski and blah blah, so pretty much in the snow. Now what we have is we have this one going forward. So this is pretty much the wind. Okay, that is pushing the sail forward. Now what we have is we have some sort of C. Now C is going to be friction. Okay, because the friction of the what's this of the ski on the snow. Now B is going to be the weight. Now how do we know B is the weight? Because B is pointing down. Now D is going to be the reaction force in this particular case. Okay, so D is going to be the reaction force from the ground. So the D will be, I'll just write down force from the ground. Okay, so I'll just put this one down there. Now let's look at the first one. So weight of the buggy is going to be clearly B, so therefore this here will be clearly B. The force that's pulling the buggy along, so this here is going to be clearly A, because where it's going is going forward, so therefore A is being pushed forward by the wind, it goes A. And then what's left is going to be friction between the ski and the tire, will be C in this case. Now these 3 marks, you need to get one correct for each of the marks. Let's move to the next one. Now the scientists travel at this much each day. So each day he traveled this much. Now how many kilometers will he has gone in 10 days? So we know that one day he covered 80 kilometers. So therefore 10 days we need to do 80 times 10. This will give us 800 kilometers. So therefore the answer is 800 here. Now when the sail is being used, the buggy, when a bigger sail is used, the buggy goes faster. How does a bigger help him go fast? Now let's have a look. Now how does it work? The wind is pushing on top of it, so therefore if we increase the surface area, it means what? We're going to have more wind or more air this time, therefore more force. Okay, so now what we can do here is one walk. So we can say, so bigger sail equal to larger surface area. Okay, so this big surface area, so therefore it's gonna catches more air. So if there's more air, more wind, this leads to more force. Okay, so this is the proper explanation why a bigger sail helps them go faster. Now this is nice and easy. We got the switch, so this is going to be the switch there. We got the bulb. Okay, this is what? We got 1, we got 2. So this is A, battery. This is A, look at this A there. So this is going to be ammeter. Nice one. Okay. Now for this one you need to make sure, because it's got 1, 2, 3, 4. 1, 2, 3, 4, yeah? The motor is just the odd one out. Now, give the name of the part that is the energy source. Now look, there's 1 here, there's 2 here, so therefore this here is a battery. Okay, now remember, so this here, if there's 1, it's a cell. If you have more than 1 connected together, therefore this is a battery. Okay. Now, a series circuit, parallel circuit, what happens? So we know this one as well. So circuit 1, where's circuit 1? This circuit 1, it is a series, it is a parallel. Again, series, remember series, there's only what? 1 loop. Look, there's only 1 loop. So from here to here all the way, 1 loop. Parallel circuit, there's more than 1 loop. You got this loop here, and you got the second loop there. Okay, nice one. Now, wires. It's made up of what? All the wires in your house. You cut them open. What happened? They're made up of copper wires. Nice one. Now this one here is what? Okay, we need to label this properly. Now this is going to be the moon. I'll just put the moon. Okay, put the numbers there. I'll just write it down here so this way we know. So this is the moon. So this will be number 2. This will be the Earth. This will be number 1. Okay. Now this is going to be number 4. This will be eclipse. So total eclipse number 4. And what's left will be the sun. Number 3. Okay. So nice and easy, isn't it? Okay. Now this one. Yes. So we got some serious good work there. Now, so we discovered a Sarah cycle, blah blah blah. And here are the dates. Now, if you go from this year to this year, there's 18 years. Let me zoom in. Okay, so 18 years. So from this year to this year, there's also 18 years. So therefore, from this year to this year, we should also have 18 years. So therefore, this will be 2017. Okay. Now, what's left is the date. Now, how do we know the date in this case? I discovered a regular cycle of eclipses, and here are the thing. Now, 20, 31st, 11th, and then is there anything else we need? No, nothing else we need. Alright, now, what we need to do now is we need to find out the year. Sorry, the year is done. We need to find out the month and the date. Now, let's look at the date. Now, from 20 to this, you can see that it has increased by 11. Now, from 31st to 11, it has increased to 11 as well. So there's 11 days. 11 days. Yeah, 11 days. And the first to the 11, there's 11 days. Let me just count this again on the calendar very quickly. Okay, so pretty much. So from the 23rd, so if you count 1 all the way to 11, 11 days. 20, so 21 all the way this 11 days. So therefore, we expect this to be on the next 11th day. So this would be about 20 in this case. Yeah, so 20 seconds. Now, all we left is the month. How can we find out the month in this particular case? Okay. Now, if it's only been shifted, so if eclipse 3 occurred on the 11th of August, and we expect to be shifted by 11 days in the future, so therefore this will still be the same month. So this will be August. There we go. Okay, so hopefully this helped you out. Let's go to the other one now. This is matching in size, so each observer expand blah blah. Okay, the ship is going out of sight. So if the ship is going out of sight, so you can't see the ship anymore. So this tells us that the Earth is a sphere. Okay, because if the ship is, if the ship is, if you're here, you're looking straight, the ship is going down the horizon. So therefore, the Earth is a sphere. Now we have day and night. For we to have a day and night, the Earth needs to spin. Yes, so the Earth needs to spin on itself. Okay. Now we have summer. Now if we have summer, then it means that the Earth needs to be orbiting around the sun. So the Earth needs to be orbiting where? Around the sun. So therefore it is going to be where? So the Earth orbits around the sun. Yes, but also tilted, because the tilt gives it summer, isn't it? Remember the tilt? Okay, if it's tilting closer to the sun, the summer is tilting further from the sun, is going to be, yes, the tilt and the orbit, and then the year is just this one there. Okay, so this is nice and easy. Now we have a series circuit. Now for this one here, you see there's a thing. So normally we need to be talking about C and D as well, but it was not printed, so I told some people don't worry about it. Okay, now if everything is open, what's going to happen? So this will be off, this will be off, this will be off. Okay, so if everything's open, there's no current going through. Now if this is open and this is closed, so if this is closed now, what happened? Look, so current goes through, goes here, but look, it's blocked. So therefore this will be off, 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 off because this is still open, so S1 is still open. Now we have S1 is closed, so this is closed. S2 is open, so therefore current will go through here this way. So current will go through this way. So therefore, this will be on. This will be on. This will be on. This will be on. Okay. Now, here is the intriguing part. Now, this is closed, and this is closed. Now, here we go. So this is the important one. Now, current will go through there, through A, through B. So therefore, A and B, on and on. Now, look at this. So here, current can choose to go here and go here. Now, which way do you think current will go through? Now, this one here, so current needs to go through this one and this one. But here, current can just go through the wire and back here again. So what will end up happening is the current, all the current will go through here. All the current will go through here. So this will be off, and this will be off. Now, here's the reason why. Here's the reason why. So this here, okay, let me just zoom out. So this way you can run down. So here's the reason why. So what we're going to add a reason here. Okay, so here we go, reason. Okay, so current always follow the lowest root, the lowest the root let's see, the root of the path. Okay, so current will always follow the root of path with lowest resistance. Okay, now if you remember when we did resistance, if you have to get to somewhere, so this here, look here, this is just one, there's no obstacle. So here, no obstacle. But here we got a bulb, so the current needs to go through the bulb and give it light, need to go to the other one, sorry, give it energy, and then the second one transfers the energy and come back again. So therefore, current will not go through that. So current always like to flow to the path that has the lowest resistance or no resistance at all. So this is the wire in this case. Okay, now this is why you may have seen the bird. So we got the cables. Okay, you may have seen the bird with the legs. Okay, cables there, cable there, the birds sitting up top. So we've got the birds. Got the bird sitting there, bird there. Okay, you may have seen the bird sitting on the wire. Okay, and the bird does not get electrocuted for the same reason, because current, what happens, current always follow the path of least resistance. So here the current, instead of the current going through the bird, okay, and back down again, it is much easier for the current to just go just in the wire. Okay, so that's why the birds, if the bird is touching, if the bird, so therefore the current just go through the current just go in the wire as long, because the bird has a high resistance. So the bird has a higher resistance compared to the wire. Yeah. So even if you were to be standing on the wire, so even if you were standing on the wire there, so let's say this is you, okay, the current will still go through the wire in this case, as long as it's not touching anything else. Okay, because current likes to follow the route, the path with the lowest resistance. Okay, hopefully that makes sense. So this is your bulb, and make sure you got this correct. Build the circuit there, we got the circuit there. Now, how do we know? So how can she get both of the lamp open at the same time? So therefore, for this to work, so if F need to work, so this need to be closed, okay, and then this need to be closed. So therefore, current goes through here, through here, through here, and through here. Okay. So therefore, now remember, so okay, now if we do this, for example, if we close this, yeah, if we close this, what will happen is current will go through here, here. Now, current will follow the path with least resistance. Now, this here has no wire, so therefore, here, this one has no bulb. So current will go through here and skip F. So we don't want this to happen. So therefore, we want this to close, this to close. So therefore, current goes like this. Therefore, S5 and S4 must be closed, and then S3 open. Alright, so therefore this will work. Okay, and this is a nice one, this is a nice one, blah 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 blah. Okay, now let's read the question though. Time it takes to orbit the Earth, time it takes for the planet to orbit the Sun, to get the Sun there, for him to orbit a quarter, 1 year. Okay, now blah blah blah. Now mark after 6 months, so 6 months. Okay, now let's do the Earth first. Now the Earth takes 1 year, so if the Earth goes around here, so this is 1 year. Now 6 months is half, so therefore the Earth will be here. So 6 months, the Earth will be here. So the Earth will be at this point. So this is half. So this is Earth. Yeah, that's the first one, half. So therefore, so Earth 6 months will be halfway. Let me just say, let me just write this down properly. Okay, so Earth 6 months. Oh, that's bad. That's bad handwriting. Let me just fix this up. So Earth 6 months would be half way. Okay, now let's keep going. Now Mars took two years. So Mars is here. So Mars will take what? 2 Earth years. So 2 Earth years. 2 Earth years. Okay. So 2 Earth years. So therefore, so Earth will take. So when Earth, when Earth, Mars or Mercury, was it Mars? Sorry, Mars is there. Yes, I remember. Mars is there. So Mars will take. So when Mars do one complete journey here, so when Mars does this, Earth would have done 1 and 2. Yeah, 1 and 2. Okay, so 1 and 2. Alright, so therefore twice. Okay, so twice. Okay, so we've got Mars is pretty much, yeah, so Earth is twice that. It's twice that. Okay, now we're looking for 6 months, which is what? Okay, which is what? So we got. So where will? So when? Well, 6 months later. So 6 months later is half. So therefore, 6 months later, Mars would only done a quarter, which we're going to be here. Okay, so Mars after 6 months, only a quarter. So quarter. So quarter way. Sorry, not halfway. Quarter way. Yeah, because if it's 6 months, yeah, Mars needs more than that. So in less than, therefore in 6 months, 6 months, so half that again. So 6 months would be just half there. So Mars will be there pretty much in this case. Yeah, so this would be Mars. Mars there, Earth there. Okay, and we're left with Mercury and Venus. Mercury. Okay, let's do Venus. Venus half a year. So therefore, half a year. So half of the. So therefore, wait. So it took. So this one here goes down 1. By the time it took 1, the Earth would have done 0.5. 0.5. Yeah. So this is just 6 months is 0.5. Yes. So therefore Venus doesn't move at all. Venus will just be here. Yeah, Venus is just there. Yeah, because 0.5 is what? Sorry, 0.5 is what? 6 months in Earth years. Yeah, so it would just be there where it is. Hopefully that makes sense. So Mars, Venus, stay there. Mercury will take 0.25, 0.25, that's a quarter. Okay, that's a quarter. So a quarter, yeah. So when Mercury does a loop, yeah, Earth would have taken Earth to do a quarter. Therefore, Earth would have done this quarter here. I think, yeah. So this is a full. So half quarter will be there. So Earth will be there. So Earth. So therefore, this is done. This one says done half. So in 6 months, yeah. So 6 month Earth would be there. So therefore, a quarter is there. So therefore, in 6 month, in 6 month time. So 1 year, 6 month it will be here. Okay, now watch this. So in 0.25 years, which is a quarter of Earth orbit, so Mercury will have done one loop. Yeah. Now, for and then for so a quarter for another quarter, so Earth will be here. So in 6 months, Earth will be here, and then this guy will have done another quarter, a second orbit, and Mars will be at the same point. So Mars will be there. So therefore, what we can say Mars did two complete orbit. There we go. Not Mars, sorry, not Mars. Mercury. My bad. Mercury. Yeah, Mercury. Now it makes sense because Mercury is the inner planet, so inner planets go faster. Okay. And then same thing with Venus. So Venus, when Earth did so quarter, was it a quarter of the year? So when they get there, so when Earth get to 6 months, Venus would have done one complete turn, which is go back to where it started. Okay, so stay there. Pretty much it just did one complete orbit in this case, yeah. And now this is the explanation. So make sure that if you got this wrong, this is the explanation why. Okay, hopefully this makes sense. Now let's talk about what is this one here. We got this one here. Now use information below to calculate the largest and the smallest distance between Mars and Venus. Okay, so the closest distance. Now the closest distance you're going to have between. Let me just get rid of those extra points. So this way we can have some stuff to work with. So the distance would be when Venus is here, and this would be the closest distance. We want to work this out. Now this is straightforward because we know the distance already. So we know that from the Sun to Earth, this is 15, and we know from the distance from Venus to here, this is 108. Okay, so 108. So therefore, the answer for this one's going to be 150 take away 108, and this will give me 42 kilometers. That's one. Okay, this makes sense because this is how they are closest. Now, for them to be further away is going to be 1. So if Earth is here, then further away it would be when Venus is going to be straight there. So therefore, you got this distance, which is 150, and you got this distance, which is 108. You add them together in this case, so because they're further away. So 150 plus this one, so you end up with 258 there. Okay, so hopefully this makes sense. Now calculate how long. So we know speed is equal to distance over time. We're looking for time. Time is equal to what? Distance over speed. The distance which we know from the Earth to the Sun. So this will be 150 million kilometers. So 150 million. How many zeros? Million is 1, 2, 3, 4, 5, 6 million. Okay, kilometers. We need to factor in the kilometers. So okay, you know what? Let me just leave this one kilometers for now. Kilometers divided by the speed, which is kilometers per second. So my answer. Now you see the kilometers kilometers, and the kilometers cancel out. So therefore, now I'm left with 500 second. Okay. Now we need to label where we'll be traveling the slowest. So the slowest one is going to be further away. So this will be slowest there. One will be further away, and then when it is fastest, going to be close to the sun. It's going to be here. Going to be here. Label it F. Okay. The question is why is this? Why is this? Okay. So why is this? So we're going to write down. So therefore, we're going to write down what is the comment. Asteroid. Yeah. So the asteroid is attracted by the sun's gravity. So what happens is, okay, as it gets closer and closer to the sun's gravity will affect it more and more and more, okay, because the closer you get to the sun, the stronger the gravity, and therefore it's gonna attract it to the sun, and then this will speed it up. And the further you are, the weaker the gravity, and therefore it will go slower. Okay, so hopefully this makes sense. Right. Now speed, we know. So speed equal to distance over time. Distance we know is this. This is there. We got 12.5 meters per second. Now compare the forward force on the bike with the backward when it's going at constant speed. Now, if it is constant speed, what do we know? We know that the forces are equal because they are constant speed. They are equal. Now, the bench forward. So now I bench forward and then go. What's going on? Okay, now what's going on? Now this means that the forward force is stronger compared to the force there. Now what we're going to say the following: the forward force, okay, is greater than the backward force. Okay. Now explain your answer. So now what is the guy doing when it is crunching down over the thing? What is it doing? So it is, what is it doing? What is it doing? Okay, what is it doing? Okay, so what is it doing? Explain your answer. So the reason why is because air resistance is reduced. Okay, air resistance is reduced as there's less surface area. Okay, now Galileo, your best friend. Now Galileo saw blah blah. We can see the moon. Now we got Jupiter, J. We got the moon here. 1, 2, 3, 4. We got the sun here, and then we got the Earth somewhere here. Yeah. Now, how do we see the moon in the first place? Now, for us to see the moon, okay, the light from the sun need to go to the moon. It need to bounce off the moon and come to us. This is how we see it, isn't it? And that is your answer. So therefore, we need to say light from the sun, yeah, reflect off the surface of the moon, okay, and travel to us. Okay, here we go. Now, 4 moons are approximately the same distance, and they don't have the same brightness. Why is this? Why they don't have the same brightness? Now, so this one I'm going to say pretty much we need to think of the moons. Okay, why is it? Now, let me just change one of the diagram there because we talk about this. Red color. Okay, now this is the one of the moon. Now, what if one of the moon is slightly bigger? What if one of them is slightly smaller? So how will this affect the light? So when the light from the sun is going, okay, now this guy here is more surfaces, so therefore more light is hitting it, and therefore more light is reflecting off it. So therefore when we receive this one, therefore there's more light from this one. Yeah. Now for this guy, it has a smaller surface, so therefore it only reflects a small amount of light. So therefore, here we go. When you look at yourself in the mirror, the bigger the mirror, the more you see your reflection. Okay, the smaller the mirror, the less you see your own reflection. Okay, so what we're going to say, we can say moons reflect different amounts of light due to their different sizes. Okay, and let's say n color, because they can have different color. Okay, different color, nice one. Okay, we'll come back to this one. Here we go. Find the graph. Now, for the graph, here what is what you need to do. Ethiopia distance. First of all, we need to look at the Europa. Now, what we know Europa, we know that the time is 3.6. So we're going to go. Now, time is here. We need to find 3.6 on the graph. The 3.6 on the graph is going to be where? So you got 3.2. We got okay. 3.6 wasn't it? Yeah. So we got 4. So 3 is somewhere here. So 3 is somewhere here. So therefore we got okay. So somewhere here. Alright. So therefore we need to go where? We need to go across. Okay. So dotted line, dotted line, dotted line, dotted line, dotted line, dotted line, dotted line here, and then from here we go down, 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 down here. Now in the middle we got 0.07, which is somewhere close. Therefore I'm gonna go with 0.68. Okay, 0.68 in this case. Okay, so this is what I've got. I'm very close to 0.7. If you count that 0.7, that is indeed correct. So this is how we do it. If you got this wrong, you need to see this extrapolation. Is that how you call it? Now, Jupiter, you realize that Jupiter is a model of our solar system. So Jupiter represents what? The sun. The moon represents the planets. Nice one. Now this one here, what does it do? It prevents. Now, look at this. There are two things it prevents, yeah? What does it prevent? It prevents conduction and convection. Okay, here we go. Right, now let's talk about this. Why is it good at reducing heat loss? Now the fiber, okay, what does it do? Okay, it traps a lot of air. Okay, now air, it is a good insulator. Okay, so therefore it's a good insulator. So insulator, there are materials, there are things that does not allow heat to go through them easily. So your jacket that you wear, the fat in your body, that's an insulator. Double glazed window insulator. So air, so the fiber that you have, so your jacket, even your jacket, yeah, there's some fibers in it, like cottons, sometimes with different type of fibers. So there are very small holes in them that traps air. Okay, and it does this. So what it does, it prevents heat lost by conduction. Yeah. So therefore, your body is not touching all the surfaces directly. Convection as well. Now here we have a nice circuit diagram there. So you guys should know this one already. If not, let's take a look. Now, what is the total? Okay, now we got potential difference of each cell. So we got one cell, two cell, three cell, four cell. There are four cells there. Okay, so the four cells. So therefore, 4 times 1.5. Okay, this will give us 6 volts. So the answer is 6 volts there. So therefore, all of this collectivity will give us 6 volts. Okay, nice one. Now, what is the reading of the voltmeter? Now, we know what happened. Voltage in parallel equal to same. So therefore, the voltage will be 6 volts. So therefore, the voltage here will be 6 volts because it's a parallel circuit. Yeah. Look, we can see one loop. We can see a second loop. Okay, so this is parallel circuit. Nice one. Now, what is the reading of the ammeter? Okay. Now we know that what current in parallel splits. Therefore, therefore, this current goes in, this current goes in and add up, and this one here goes back, and then they split up. Yeah. So therefore, it's going to be 0.2 plus 0.1. This will be 0.3. Answer 0.3, and this is the working out. Hopefully, this will make sense to you. Now, the resistance of the lamp is what? Now, let's take a look at it. Let me just delete this. Okay. Now, let's think of it logically. The resistance of the lamp. Okay. Now, let's have a look. Now, this resistor, this here is the resistor. Look at the amount of current it's getting, 0.1. Now, this is the bulb. Look at the current it's getting, 0.2. So this tells me that the resistance R of the bulb must be lower than the resistor, because current likes to go where there's least resistance. So since the bulb has least resistance, more of the current is going through the bulb. Okay, so therefore the resistance of the bulb is smaller than this, and here are the reasons why I told you. So therefore, because the bulb, okay, or the lamp, okay, gets a larger amount of current, okay, than the resistor. Okay. Let's take a look what we got. Okay, now we have this particular question here about the runner. Now, A, what's happening at A? Now we know A, what's happening? A, it is speeding up. We can see that the speed is going from 0 all the way to 10 at A, so therefore A, it is speeding up. Okay, now B, the graph shows what? B, it is staying at the same speed. So B, it is moving at a steady speed. And C, it is what happened? It goes from 10 all the way down to 0 speed. So therefore this is what? This is slowing down. Okay, it's slowing itself down in this particular case. Now let's move to the next one. Where are we? Okay, now calculate the gradient. Now what we need to understand, that the acceleration is the gradient. The gradient is the change in y over change in x. So therefore, in the first 4 seconds, so first of all, I'll get rid of that. Okay, we're going to zoom in. We're going to see where the first 4 seconds are going to be. And the first 4 seconds is here. So therefore, I have my straight line. Therefore, this line here, this is my change in y, and this is my change in x. Yeah, and this is my triangle. So therefore, I have the line here. Let me just draw the line. So this is line A. Therefore, I have this line here, which is my change in y, and then I have this line here, which is my change in x. Okay. Now change y, we go from 0 to 10, and then change x, we go from 0 to 4. So therefore, I have 10 take away 0, and then I have 4 take away, 14. No, that's wrong. I got 4 take away 0, so I have 10 over 4, and this will give me 2.5. Now I need to put the units. The unit is going to be meters per second squared. Nice one. Next one, we have this one. So 60 watts means 60 joules every second. Okay, so this means that in 1 second we get 60 joules. So this whole thing, we call this 60 watts. The question is how much energy is giving out each second. So we know that 1 second is giving off this much energy. So therefore, the answer is 60. Okay. Now, what energy is being used? Now, question is, what do we put into input? What do we put into the bulb? We put electrical energy. Okay. What do we get out? What do we get out? We get light energy, and then we get some heat energy. So therefore, we got electrical energy, light energy, and heat energy or thermal energy. I'll use the word thermal energy because it's much better in this case. Okay, now some energy is wasted. Why is some energy wasted in this case? Okay, now some energy is wasted, so we've got unwanted energy, unwanted heat energy. Okay, produced. Produced. Do we produce, make? I'll say. Let me just change this. Okay, so the bulb is transferring some heat energy and is unwanted. We can't use it, so therefore it's wasted for us. This is the last question there. Work out the resistance of the filament bulb when it is in use. So therefore, now the equation here you need to remember. So this equation was visible. So P is equal to I. Oh, okay, I think, wait, that's the wrong one. Sorry. The equation is V is equal to IR. We need to rearrange for R. R is equal to V over I. V is 12. R is 3. R is 3. Did I do this correctly? Did I do this correctly? Let's check. Yeah, so therefore R is 4. Yes, 4 ohms. Okay. Anyway, let's keep going. Now this one we got the equation P is equal to IV. Now we're looking for the two bulb there. So therefore it's going to be I. It's going to be 3 plus 3 times 12. So it's going to be 6 times 12. This will be 72. 72. Now this here is a parallel circuit because we've got one branch here, one branch there. So this is 3 amps. So this is 3 amps. Therefore, the total current that goes in is going to be 6 amps. So we want to work out the power supply to those two. So therefore, we need to factor in current has been split up. So 2 there. Okay. So therefore, we have 674. Now this one we know energy power is equal to energy over time. We're looking for time, so time is equal to energy over power. Energy, we know it's 72 kilo divided by power, which is here, which is 72, and this will give me 1000 seconds. So therefore the answer is 1000 seconds. Again, if you got this wrong, make sure that it's fixed up properly. Okay, so hopefully we're all controlled, hopefully we're all awake, hopefully we know what went wrong and how to fix it in the future. Okay, thank you very much.